So it should be recording there now. Basically, we'll get started. Just thought I'd introduce myself a little bit. So my name's Brayden. I am a third-year environmental geoscience major here at UNB. So I've taken this class before. I've taken some other classes, all pertaining to science. I really enjoy this stuff. A few things about me. I enjoy photography. And like any good geologist, I have a mineral collection. So as you can see, these are a couple of pictures I've taken. I enjoy hiking. So this picture I took with some friends while I was hiking this summer in Fundy National Park. And then here's a picture down by a beach by St. John, and it's got these really cool bedding structures. So if you end up in the future taking sedimentology or anything like that, or even I think in this course a little bit, we'll look at stratigraphy and stuff like that. You'll kind of understand what's going on with those beds there. But I won't get into that tonight because I'll spend all night just talking about that. Another interesting fact about me is before I started university, I actually lived in Tahiti for 2 years in French Polynesia. And so that's this little dot here in the middle of nowhere, pretty much in the middle of the Pacific Ocean, kind of about halfway between New Zealand and Chile. So that kind of played into my love for geology and why I'm doing this. And then just over here is my email. So if you have any questions kind of pertaining to PAL, or if there's something you'd like me to cover in a session, you can send me an email over there, and I'll make sure to include that in my next PAL session. So yeah, that's me. So before we get started here tonight, I don't know, has anyone heard about the current volcanic eruption going on right now in La Palma? Jarek, have you heard of that? Have you seen any news about that? I see we have Caroline with us as well. Welcome. Okay, perfect. So yeah, there's been a pretty significant eruption going on kind of the past week in La Palma. So it's they've had lava flows, and so earlier this week, this video here we'll watch. It's just a couple minutes. It actually the lava flows actually started to hit the ocean this week, and so I thought that was kind of neat. And actually, I think just yesterday or the day before, they actually had a couple other eruptions start off of this same volcano, kind of a vent that came off the side of not the main eruption point, but a new vent that's formed. So they still have a continuing eruption going on. So I'll just start that, and if let me know if you can't see it or anything like that. So yeah, it was just something I thought was kind of neat. And there's lots of you could spend hours on YouTube right now. There's tons of footage of this eruption that's ongoing and kind of the hazards and stuff that it's causing for people with the toxic gases and ash and stuff like that that's accumulating. So um, feel free to check that out some more. So I guess before we start, do either of you have any questions specifically? You're welcome to type in the chat. You're welcome to unmute yourself and talk. Kind of the way I wanted to set up the session tonight is just kind of we can chat, we can discuss topics. I've got some questions and stuff we can work through, but before we get started on those questions, I guess, do you guys have any questions for me? All right, I will take that as a not right now. So we'll get started. So one of the first questions I wanted to explore today was what evidence do we have for plate tectonics? So I know in the lecture this week we talked about a number of things that kind of pieces of evidence that we had for plate tectonics. Did you guys know what any of those are? Feel free to, if you want to throw it in the chat, or we'll see if we can come up with a bit of a list here. Okay, yeah. So earthquakes would be a piece of evidence that we need something that explains those. Fossils, yeah. So fossils is a big one. Let's see, can I write on here? All right, perfect. But yeah, fossils was a big one because I don't. If you guys remember, we talked about Alfred Wegener, and he was this meteorologist actually, but he started kind of looking at the Earth and how things kind of fit together, and that was something that he'd noticed was he'd look at the kind of the continents or the border there in South America, and he looked at kind of some of the fossils that were found there along the border of Africa, and he noticed that some of them matched up, and so he was trying to explain how exactly that all fit together. How could these fossils be on both sides? So we have fossils. We have yeah, you could argue glaciers as well in a sense. Kind of some of these formations might have been seen on both continents. So I'll put some other notes over here. Yeah, complementary coastlines. That's a big one. Kind of like a puzzle piece, I guess you could say. Like I think what you're getting at is when you look at the map, you can kind of look at the world map, and it kind of looks like everything kind of fits together, right? So that was another big piece of evidence that Wegener used. Was he talked about how the complementary coastline. So I'm going to call that fits together like a puzzle. Yeah, volcanoes. So volcanoes helped us understand a little bit about those margins of where the plates are defined, because volcanoes for sure we would see them kind of and we'd need something to explain where the magma and stuff is coming from. And they'd come along the coastlines there, kind of specifically along the subduction zones, and we'll talk about that in a little bit. But yeah, volcanoes kind of provide us some evidence that there's something going on. So there is a couple other key pieces of evidence that I also wanted to mention. That so one of them is being polar wandering. So we've known that the North Pole kind of it wanders. It doesn't kind of stay put in the same spot. And so, but what happened is when a bunch of scientists in North America, they kind of mapped out the polar wandering, and then a bunch of scientists in Europe, they also mapped out the polar wandering. They didn't really add up. You kind of ended up with like two separate polar wanderings. So that either meant two things. It either meant that it meant that there was two North Poles, or that the continents had moved from where they were at the time that signature was recorded. And I guess when I talk about the signature being recorded, what I mean is that certain rocks we talked about a little bit briefly. I think Dr. Shaw mentioned the Curry Point. And so that's something that as a rock cools, it's actually able to, at a certain temperature, record the magnetic, if there's magnetic minerals and stuff inside it, it's able to record the direction of the North Pole. And so polar wandering, that was a big part, along with magnetism. That was a big proof for that the continents had moved, that they weren't where they originally were. And then I'll just throw in the final piece of evidence that I had in mind was seafloor spreading. And so seafloor spreading was discovered kind of in during the Cold War, while they were doing a bunch of mapping of the Atlantic Ocean. And so while they were doing this mapping, they had basically a device that was detecting, and they noticed that the rocks kind of flipped back and forth, or at least the North Pole kind of did, and it kept flipping back and forth, showing that the rock hadn't all formed at the same time. And what was even more interesting is that it was kind of equal on both sides of this central ridge. And so what they discovered is that the continents were slowly getting further and further apart, that North America and Europe were slowly getting further and further apart. And now we've been able to do all the calculations and figure that out. And we know that it's about 2 to 4 centimeters a year, about the rate that your fingernails grow at. So those were kind of the key evidence points for plate tectonics. So if there's no questions there, we'll so this is missing one key thing, which we'll get at here in a minute. I think I have a slide on it. But all of this evidence, the problem was it was missing a mechanism to basically show how this worked, because the way that Wagner saw it was that his theory was that the continents were just smashing through the ocean crust, which we know that it doesn't really make sense. So nobody really adopted his theory, and it wasn't until we realized the seafloor spreading theory that the seafloor itself was getting bigger. But we also needed some other ways to account for that, because we know that the Earth isn't getting larger and larger. So the next question I had is, I just wanted to draw some quick sketches of kind of what the plate boundaries look like. So if you want, you can give that a try on your own. I'll give you a minute or two. But maybe before we start, maybe in the chat, do you guys remember what the three boundaries are? Do you know what they're called? So those are the three main boundaries. And let's see. Does anyone want to try maybe just sketching that out quick? And I don't know if you want to like snap a picture and throw it in the chat maybe. Just a rough sketch of kind of like what the they kind of look like roughly. It doesn't have to be. I'm not an artist. I'm not gonna. Doesn't have to look great. Just kind of give us a rough idea of what those three different boundaries look like. Next time I'm going to try to get the whiteboard set up so that we can kind of draw together. Yeah, figured that out yet. Oh, so there's my drawing. Skip to the next slide. But if we wanted to sketch them quickly, essentially we would have our kind of transform boundaries. So this would be kind of looking from the top, and the faults are kind of sliding across each other. And then we have our divergent boundary where kind of the faults are coming apart. So here we're actually kind of creating new rock if you want to think about it, but we have kind of this divergent, this rift valley. Here, I'll just draw them. Like I said, I'm not an artist. They're kind of whoops. They're diverging that way. And then we have our convergent boundary, which would also be, we could also call it a subduction zone. So you've got typically you've got crust or an oceanic plate, and you've got an oceanic plate subducting under the other one. So a little more clearly, I have a diagram here of what that looks like. And so these, especially along kind of these boundaries, we're going to talk about earthquakes and stuff a little bit. These boundaries kind of play a big role in earthquakes and why we get them. So coming back to so we talked about the evidence that we have for plate tectonics. Do you guys remember what would be the main driving force for plate tectonics? What was that piece of basically that mechanism that Alfred Wegener was missing in his theory of continental drift? There was one key mechanism that he was missing to explain it all. Yep, exactly, convection. So convection, we know that the mantle is a solid, but it acts kind of like a solid solution, kind of like a fluid, and so it convex, kind of like a pot of boiling water. You have as the water heats up, the warm water wants to kind of rise to the top, and then the cool water sinks, and then that gets heated up, and it kind of creates that circular cycle. And so because the plates are kind of sitting on top of the mantle, right on top of the mantle, you get this kind of pushes up at the ridge, and then it kind of pulls. They call it slab pull as the slabs are pulled under in subduction zones. And so that's kind of the key important thing to remember when if you're asked on a test or on an exam, kind of what is the driving force of plate tectonics. It's going to come back to convection, and it's an important concept that'll keep coming back. So looking at earthquakes a little bit, something that often we get mixed up is we hear the term epicenter and we hear the term hypocenter, or sometimes the hypocenter, we call it the focus. And so they're similar, but they're not the same thing, and they often get mixed up. So can anyone remember the difference between the two. That's all right. So the difference really is the epicenter is, so they both talk they kind of both pinpoint where the earthquake originated from. But when we're talking about the epicenter, we're talking about kind of where the earthquake originated from in reference to the surface of the earth. Whereas when we're talking about the hypocenter or the focus, we're talking about, oops, yeah, we're talking about this part right here. So we're talking about that area in the middle, kind of that really origin in the ground, but the epicenter sits directly above it. And so that's something that sometimes they often get mixed up, but yeah, just remember that the epicenter of an earthquake is on the surface and the hypocenter is down kind of in the actual fault down in the earth. My next slide, there we go. All right, so we talked about 4 different types of waves. Maybe before we get into what those 4 waves are, those 4 waves are broken into 2 categories. Do you remember what those 2 categories are? Exactly, yeah. So we break up our waves into surface and body waves. And exactly. So the first couple types of waves we have, they're S and P waves. And we also have 2 types of surface waves. Yeah, we have love waves. Yeah, and Rayleigh is the last one. And how do I have it over here on the next slide. I always spell Rayleigh the wrong. So yeah, here we have our P waves, our S waves, our love waves, and our Rayleigh waves. And so these 2 over here, I don't know if you can see there. Is that a laser pointer now? So these 2 are our surface waves over here. And over here we have our P waves. And so the P wave, or sorry, our body waves. So the P wave and the S wave, they travel through the earth, whereas the love and the Rayleigh waves, they kind of travel over along the surface of the earth. And just kind of as a fun question, I don't know if we necessarily went over this exactly in class, but do you guys know which waves are more destructive? Like not out of the 2 types of waves, out of body or surface waves, do you know which ones are more destructive? Okay, we got to vote for S waves, so body waves. Yeah. So actually, and I was kind of surprised when I first learned this, the most destructive waves are actually going to be our surface waves. And it's because it's kind of, they act very similar to the way that the ocean waves would act, except that in this case, you kind of got the direct surface of the Earth that are getting really bombarded by these really destructive waves. Whereas the P waves and the S waves, they're still really important to the earthquake. They're kind of passing through the Earth, and so they're not nearly as destructive as our surface waves. So this is a demonstration. I don't know if you guys have seen this demonstration before. When I took this course, this was something we did in class. So my professor, they brought in a big slinky down to the front of the class, and we had a bunch of volunteers. But it's kind of a cool demonstration to kind of demonstrate the difference between P and S waves. So we talked about this a little bit, where P waves, there are compressional waves, and S waves are shear waves. And sometimes they're also called our primary or our secondary waves. But I'll pop this on, and it's just kind of like a little demonstration of how these waves. So here we have these, now they've switched to S waves. So yeah, that first little part here where they're going, where it's kind of pushing back and forth or compressing, those are what our P waves kind of do. And then we get to the second part where it's doing kind of that shearing, and those are our S waves. So I guess before I go, is there any questions kind of about waves or anything like that? Yeah, well, if they will keep going. So this is kind of a typical seismograph, and so can anyone, basically, I will put kind of got 3 sections on it. If we were looking at the seismograph, can anyone tell me what kind of waves would be at A? So we're looking at, and in this case, I guess I'll narrate. So we're going to have 3 options, essentially, are going to be P waves, S waves, and surface waves. We won't break the surface waves up into Rayleigh and Love. So just give another second. All right, so if you were looking at a seismograph, then the way that you would basically determine what's what is these first group of waves here. These are going to be your P waves. And the way I like to remember it is the P waves, they're your primary waves. So they come first. And we know that the P waves actually will always come first because the P waves travel slightly faster than the S waves. And that's what gives us our lag time between the P and the S waves. So we have our P waves here. And then over here at B, we have our S waves, our secondary waves. And then over here, we have our surface waves here at C. And here's actually where you can see, we were talking about what kind of wave is the most destructive. And you can see just by the amplitude of this wave, so the kind of the change, like this distance here, is a lot greater in these waves than than anything else. And so this is what this shows us just right on the seismograph how much more destructive and how much more damage the surface waves can cause. So I guess I have one more question here on waves, and then we'll look at some earthquakes and stuff like that. So this last question is, what are shadow zones? And at the same time, if you want to answer why they exist, or if you just want to answer one of the questions or the other, but if you want to throw that in the chat, what are shadow zones? If you're not sure, you can also just throw in the chat, I'm not sure. So, okay, perfect. So shadow zones, I think we touched on it briefly, but they're kind of important. Well, they are important. They help us understand what we actually know, why the Earth is made of what it's made of. Like, how do we know that the Earth is solid? How do we know that parts of it are liquid? We actually know that from shadow zones. And so here, maybe, yeah. So does anyone remember what kind of waves pass through a solid? Maybe a better question is, which wave only passes through solids? I asked two questions and now I don't know which. Excuse me, which one you're answering. There we go. Yeah, S waves only pass through solids. So yeah, when we have our S and our P waves, we know that S waves, they can only pass through solids. And that's because they're kind of our shear waves. It's like, I'm going to use the analogy that Dr. Shaw used, but he was talking about how in class that if you have if you go through water, right, you can kind of push the water and the water will kind of push away from you and kind of so you can compress it. But if you tried to like take a knife and slice it through the water, shear it, it's not going to do anything to the water. There's not going to be really any waves that are going to be, other than maybe your upper arm generating more compressional waves, more P waves. But so because of that, the way that the nature of the waves, they can't pass through liquid S waves. And so when we look at, if we had an earthquake here, and here we've got kind of the epicenter here on the surface, which means the hypocenter is going to be directly below it somewhere if we had a fault drawn. And so when we have basically different, we have different seismic stations all over the world, we can pick up these waves. And what we notice is that over here we've got this big S wave, this big zone where S waves aren't detected. Because basically as they hit the outer core is liquid, and so they can't pass through the outer core. And then P waves, on the other hand, they can pass through a liquid, but due to the changes in density and stuff like that, they actually get refracted and bent slightly. So they actually end up having a bit of a shadow zone as well. And so, yeah, we get this kind of, with P waves, we get some refraction. And with S waves, we just kind of get this, they just don't pass through the liquid at all. And that's how we know, that's how we were able to determine that when we're talking about the core, we have the outer core, which is a liquid, and we have the inner core, which is a solid iron core. And that's also how we know that the mantle is actually a solid, which I know can be kind of hard to think about because it's convecting and stuff like that, but I promise you it is a solid. So are there any questions there before we move on to the next little bit? All right. So we're going to look at kind of earthquakes now. So we looked at kind of a little bit of earthquakes, kind of the important parts of mechanically how they work, the S wave, the waves and stuff that they generate. And I guess, well, one more thing about seismic waves. How many seismic stations does it take to detect the epicenter of an earthquake? Exactly 3. And so yeah, you got to have your 3 stations, and they do the math. They calculate the circumference of whether they're coming from the distance, and you can kind of triangulate the position. Exactly. So yeah, now let's. So we talked about 2 different types of scales, and these scales are important in understanding the effects of an earthquake. So we have the Richter scale, and then we have the modified Mercalli scale. Basically, I'm wondering, like, what is the difference between the two, and roughly what are they? What do they measure? Yeah, exactly. So yeah, a Richter scale, it measures really the energy released or the magnitude, but that's all it really tells us. Whereas the Mercalli scale, it can tell us more of the damage or the intensity of the actual earthquake, how it actually impacted a specific area. So here I have just kind of a couple of little representations. So yeah, we've got, and this has some of the most prominent kind of earthquakes, kind of examples of different magnitudes of earthquakes listed over here, and their energy equivalent listed over here. And then over here we have the modified Mercalli scale. And the modified Mercalli scale, yeah, it's largely based on eyewitness reports of how people felt, the damage, and stuff like that. Whereas this is more of our quantitative number, really telling us, okay, here's the amount of energy that was released. And so this this leads into my next question. Yeah. So when we're talking about the Mercalli scale and the Richter scale, one of the things we can realize is that it doesn't, just because an earthquake of the same magnitude happens in 2 different places, it doesn't necessarily have the same effect on those 2 places. And so there are 3 main factors that influence the intensity or the perceived intensity of an earthquake. And so what might those 3 factors be? Yeah, exactly. So we can have, so we've got, so we have depth, we have surface geology, and I will say, so magnitude, it does affect, of course. It's gonna, if you have to have a higher magnitude earthquake to have a bigger influence on the damage that's going to be had. But there's one more factor that I had in mind. Just thinking, so magnitude, it does affect it. But what happens when we have, let's say theoretically we had a magnitude 9 earthquake in California, but then we had the same magnitude 9 earthquake in somewhere like Haiti. what factor influences, because we know that one is way more destructive than the other. There's one more factor that kind of tells us why it is so much more destructive. And surface geology, that is one big one, the depth that the earthquake occurs. But yeah, if we had two earthquakes that were the same magnitude, what other factor might play into? Yep, I mean, yep, population. You guys are making me think of extra ones. Population would fit in there, because if you had an area that didn't have anyone living there at all, then the perceived damage isn't. There's going to be nothing there to destroy. And then I'm thinking of there's one more that has to do with building codes and things like that. Yeah, so the height of the buildings could affect it. What it can come down to, I guess what I was thinking of was kind of the human factors. So yeah, the height of the buildings, or the infrastructure, and so that can be a variety of things. So that could be like the height of the buildings, the foundation. There's actually some buildings now that claim to be earthquake proof because they've kind of been built on these like springs type of things. But yeah, essentially, especially when you're comparing something like the infrastructure in San Francisco, where they're preparing for earthquakes all the time, they have a lot stricter building codes on the type of buildings that can be built, and they try to design them to withstand earthquakes. Whereas compared to in areas like Haiti, they don't necessarily have the same type of regulations on trying to make sure that their buildings will necessarily withstand an earthquake. But also surface geology also plays a very big part in that. I know in class we looked a little bit kind of about how Haiti was the most largely impacted areas. They were built on sand and mud. And that actually comes into my next question, which is what is liquefaction? Yeah, so we have when the mud or like soft ground turns to liquid when an earthquake happens. Yeah, pretty much. So essentially what happens is, right, you have all these little particles. So when you build on sand, right, like when you build on a rock, it's a rock. But when you build on sand and mud, there are a bunch of little particles. And what happens is as the earth shakes, they kind of, any water that might be in the ground, they kind of come in and fill these voids. So really, like I said, I'm not an artist, but they're kind of filling in these voids, and those particles become separated. And so then buildings and stuff, they start to sink into the ground, and they don't withstand very well. And so that's why I guess I kind of answered my own question there with the second part, but why would a house built on bedrock be less damaged after an earthquake than a house built on sand or mud? Well, it's because of the liquefaction. It's because something that's built on a foundation of sand and mud, the earth starts to shake, starts to liquefaction kind of occurs, and the buildings start to sink and collapse. Where if it was built on bedrock, yeah, it might get some damage, windows might crack, some stuff might happen, but your whole foundation, your whole building is not going to sink into the earth. And so here are a couple of pictures that I'd picked out. This one actually over here is one that I've seen quite often in textbooks after an earthquake. I don't exactly know where this earthquake was, but you can see that the whole soil just kind of liquefied and the whole building just kind of fell backwards and collapsed. And over here you have some cars. The same thing kind of happened. The liquefaction occurred, and the cars just started to sink into the ground. So my next question is, can earthquakes be predicted? Can we predict an earthquake? Exactly. So no, we can't predict an earthquake. However, you might be able to argue that we could. Some might say that we could forecast an earthquake, and that would be kind of looking at, okay, we've had an earthquake happen over here, or like if we had. So if I drew a little fault, so if we had like a fault, we could say, okay, we've had an earthquake happen over in this area, and we've had an earthquake, a fairly large one, happen over here. And so we might say, okay, well, the next earthquake is probably going to happen in this zone right here. But as for predicting it, we can't really say. It's like it'd be like the Farmer's Almanac or a long range weather forecast. We can't say, oh, an earthquake is going to happen here tomorrow, or even in the next 5 years, there's going to be an earthquake here. So seismologists, scientists, they look at this all the time trying to do their best, but we can't really predict when an earthquake is going to happen. So I also want to talk a little bit about tsunamis. So I guess for starters, what is a tsunami, and what causes a tsunami to happen? Is it the same thing as a tidal wave? Yeah, not the same thing as a tidal wave. Okay, good. So what is it then? Yeah, exactly. So it's caused by, displacement from fault movement, um, or often you could even say most of the time they're caused by an earthquake. And so either that earthquake caused, so there was a tsunami that happened out in Newfoundland and destroyed one of the first transatlantic cables they had. And what happened there is there was an earthquake, and that earthquake caused a big part of the fault to kind of shift and to collapse. And so that displacement of added material kind of caused this big wave to be created, and as it moves into shore, it becomes larger and larger. And so they often are caused by earthquakes that happen in the middle of the ocean, and those earthquakes are often, well, we know that an earthquake is caused by fault displacement. So exactly. The Jarek is typing to a question. Meantime, we'll look at the next question. So can we predict tsunamis? So we know we can't predict an earthquake, but can we predict a tsunami? Yeah. And how can we predict the tsunamis? And I guess here a more in-depth question. Can we predict a tsunami like weeks in advance? Or kind of what's the time frame of predicting a tsunami? Still typing. Still getting used to this whole virtual thing. Not sure. Okay. Yeah, we know what happens after an earthquake occurs. So yeah, in answering, so basically, I kind of comes back. So yes, we can predict a tsunami, but we still can't predict an earthquake. So we can't predict weeks or in advance that, oh, there's going to be a tsunami in a couple weeks, because we can't predict an earthquake. But we can predict a tsunami, and usually it's on the matter of anywhere from 12 hours at the longest to 1 hour at the shortest or less. So we can predict it in a matter more of on an hourly time scale. And so actually, so I talked about at the beginning a little bit that I lived in French Polynesia or in Tahiti for a couple of years. And let me see if I go back to that slide at the beginning. You can see, 1 second. So when I was there, we would often get trained on what to do if there was a tsunami, because as you can see, it's kind of right there in the middle of the Pacific Ocean. So if we had an earthquake over here in New Zealand or in Tonga or in Chile or in Hawaii or up by Alaska or even up in California, any type of earthquake, if it was generated over there, we had so much time before it would reach us. And so while I was there, this actually on this last slide, it's all in French and Tahitian. Don't worry about that. But essentially, this is one of the documents that was given to us, and it talks about, so it's really small print here, but it talks about basically if an earthquake happened somewhere up by Alaska or Hawaii, we had about 8 hours to get up to high ground. And if it happened over in Chile, we also had about 7 or 8 hours to get to safety. The scary ones is if we had an earthquake that would happen in Tonga, and there's a big fault. The Marianas Trench runs through there, a big subduction zone. So if we had an earthquake that happened there, we only had about an hour to get to safety before the tsunami waves would start to hit us. And so basically, yeah, now we have seismometers. The way that we detect these earthquakes is we have seismometers on the ocean floor, and we have these buoys that kind of sit and detect changes in wavelength. And so they're able to kind of tell us when something gets out of whack, and all of these things they're transmitting to satellites, which then transmit all the data to seismic centers and tsunami prevention centers throughout the world, and they're able to process the data. And when they see, okay, well, earthquake just happened here, oh, it looks like we have a tsunami that's being generated, they can then warn the different places to watch out. So luckily, while I lived there, I was there for 2 years, we never had a tsunami. I never had to worry about it. But I was glad to know that if something were to happen, if there was an earthquake, that we were able to predict it, so I would have time to climb up the mountain to safety. So that's what I prepared for tonight. Do either of you have any questions based on something we went over or something we didn't go over? Anything at all before we end this session? Okay, perfect. That was my next question. My next question was actually going to be, was this helpful? Did you find this helpful at all? So I'm glad that was able to help out tonight, Jerica. And I think the PAL session schedule, I think you guys all have that. So Luke will have a session tomorrow night. I believe it's in person. And I will have sessions Tuesday and Wednesday in person. And then I will be back next Sunday virtual again, I believe. If there's any changes to that, though, Angela will, of course, she'll send out an email if there's any change to that, but I don't think there should be this week. All right. Well, I will. That's it for me tonight. So thank you guys so much for coming, and thank you for participating. A lot of the way I try to organize my PAL sessions, it really helps when I have people who want to answer the questions and work through them together. So thank you both, and yeah, we'll end it there. So have a good night.